one of the best things about learning epidemiology is that you learn these short little phrases that you can use as shortcuts for different logical fallacies that people make. And you can find someone talking about a study and they might say, oh, well, maybe it's possible that the people who had the disease sit there and think about their past exposures and they might remember things differently than the people who didn't have the disease. And it takes a few sentences to explain it, but you can sit there and say, oh, yeah, maybe there's rumination bias. And so we get these cool little shorthand lingo we can use. And one of them is the idea of the ecological fallacy. This falls under, I think, the idea that correlation is not causation. These data would look really convincing to somebody who doesn't have training in statistics or in epidemiology. These are older data, but they tell a very tantalizing story. The more fat that you eat, the more likely you are to die of breast cancer. That's the way that data like this would get be understood or heard by most people. And the data come from, you take data from different countries. Here's Portugal right in the middle. And in Portugal, the average dietary fat intake is somewhere around the mean. And the average age-adjusted death rate for breast cancer is somewhere around the mean. And when we look at this and calculate a correlation coefficient, remember we said look at the empty space. All of these countries are above the mean for fat intake and above the mean for breast cancer death, positive. All of these countries are below the mean and below the mean, positive. And we would see a very strong correlation coefficient. However, we have to think about what this means. Is it real? What could possibly be driving these data? Well, there's lots of different things we could do to critique this graph. First of all, we know now that just talking about fat is kind of silly because there's good fats and there's bad fats. If I'm eating bacon grease in my coffee, the bullet coffee, versus if I'm pouring coconut oil in my coffee, totally different game. Or olive oil or butter, totally different game. They're both fat, but they are totally different effects, especially when it might come to a disease like breast cancer. If you think a little bit, what if I started the slide with no label on the x-axis? And I said to you, look at these countries. Could you put a label on the x-axis that would sort the countries in this order such that you see countries like this over here and countries like this over here? You could put all sorts of stuff on there. I mean, the simplest thing might be some label like this, or it might be something like this, or it might be something like clean water. Who knows? There might be something else that's totally grabbing this, carrying this relationship, some other confounders that are in here. When you make causal statements based on these type of data, you commit what's called the ecological fallacy. And the ecological fallacy is when you look at data that are aggregated and then compare the patterns or observe the patterns in the aggregate data. Look, say this is country A, country B, and country C. What's going on in each country? They just look like little blobs. You can probably barely see it. So if this is a blob, what's the correlation? 0. If this is a blob, what's the correlation? 0. If this is a blob, 0. I put all these zeros together and it looks like 0.9. So beware of the ecological fallacy. You can't look at the countries. Countries don't get cancer. People get cancer. You have to look at the individual people. So when we think about these aggregate data, it might be useful as a preliminary step, as hypothesis generating, as an exploratory sort of step. But don't draw causal inferences from such aggregated descriptive studies.